say you're discussing the reaction where calcium carbonate is decomposed into calcium oxide and carbon dioxide. So take limestone and you can create quicklime, which can be used to make plaster. Now, you can find in the back of the book the heats of formations of a variety of compounds, and you can also find the entropies of a variety of compounds. Our question here is this reaction going to be spontaneous at 25 degrees Celsius? And then, second, we'll ask, at what temperature will that reaction become spontaneous? In order to determine spontaneity, we need to be considering delta G. And so, we need to calculate for delta G at 25 degrees Celsius, at a certain temperature. But to do that, we need the heats of this reaction, and we need the entropy change of this reaction. And so we need to get these values from those values which are in your appendix. So go ahead and solve for the heat of this reaction first. You recall that the heat of the reaction is equal to the heats of formation of all the products minus the heats of formation of all the reactants. And so consider the coefficients in those reactants. They are all 1. And then use their heats of formation and plug in, and you can find the heat of the reaction is equal to positive 177.8 kilojoules per mole. And you also recall that the entropy change of a reaction is equal to the entropy of the products minus the entropy of the reactants, and account for the coefficients in the balanced chemical equation. You find that the entropy change of this reaction is positive 160.5 joules per Kelvin mole. So, will this reaction be spontaneous at 25 degrees Celsius? Well, first, I'd be interested in just what are the signs of these two things. Here you have a positive delta H. That is, this is an endothermic reaction. It absorbs heat from the surroundings. That does not support spontaneity because it decreases the entropy of the surroundings. It cools them down. But there's an positive entropy change for your compounds. They are increasing entropy, so that supports spontaneity. And so we have two things, one that doesn't support spontaneity and one that does. So we know that these are counteracting forces, and whichever wins depends upon these values and the temperature. The spontaneity of this process depends upon the temperature. But first, will it be spontaneous at 25 degrees Celsius? Well, plug in your delta H and your delta S values and your temperature. At 25 degrees Celsius, you're plugging in Kelvin. That's 298 Kelvin. Please be sure when you're plugging into delta H and delta S that you are consistent in values. You must either be both in kilojoules or both in joules. You must be consistent. Here, we've chosen to use kilojoules, so we changed the positive 160.5 joules per Kelvin mole into 0.1605 kilojoules per Kelvin mole by dividing by 1,000. So you plug in and you find that the delta G of this reaction at 25 degrees Celsius is 130.0 kilojoules per mole. This is a positive value. So we know that the reaction is not spontaneous at 25 degrees Celsius. Now our question is, at what temperature will that reaction become spontaneous? So we need to say, yes, at 25 degrees Celsius, it's non-spontaneous. Now, maybe at some higher or lower temperature, the reaction will be spontaneous. Having a positive delta H and a positive delta S, you might recall that in order to be spontaneous, you need a high temperature. So we'll need to have a higher temperature in order for this reaction to become spontaneous. Now, below that temperature required, you're non-spontaneous, and above that temperature you've required, you're spontaneous. The question is, at what temperature will it become spontaneous? At what temperature will it cross? Will the reaction cross from being non-spontaneous to being spontaneous? That temperature is where you're crossing from positive to negative delta G, where your delta G is equal to 0, where that reaction will be at equilibrium. That's where it crosses from non-spontaneous to spontaneous. And so, actually, before we get into that, well, actually, okay, and so we want to say at what temperature will it be non-spontaneous, become non-spontaneous, at what temperature will delta G be equal to 0. So we need to solve for what temperature. Plug in everything else and rearrange the equation, and you get 1108 Kelvin, or 835 degrees Celsius. You need to heat up this limestone to 835 degrees Celsius in order to make it decompose significantly. I guess the Mayans, they used to have to convert this calcium carbonate in their soil, that limestone, into calcium oxide to make plaster to cover their pyramids. But in order to get that reaction to proceed, in order to make that plaster, they had to heat that limestone up to 835 degrees Celsius. They had to cut down a lot of trees for that to happen and burn them. And so that is one reason why supposedly their civilization collapsed, because they cut down all the trees and they had then a drought. Now, going back to here, I'd like to talk about two terms. Below that 835 degrees Celsius, we have a positive delta G. We know this is non-spontaneous and not thermodynamically favored, but I want to introduce the term endergonic. This is just another term for saying non-spontaneous. Positive delta G. And also we'll introduce exergonic. This is saying that you have a negative delta G. The reaction is spontaneous. And we'll use those later when talking about, I guess, reactions in the body. All right, now consider another case where instead of having that chemical reaction, let's just have a change of state. Now, water boils. It vaporizes. And it has an equilibrium at 100 degrees Celsius. Below 100 degrees Celsius, the boiling of water is non-spontaneous. It really doesn't occur very much. And above 100 degrees Celsius, it is spontaneous. It occurs significantly. This boiling point of water, this is where you cross over from being non-spontaneous to spontaneous, where you cross over from being positive delta G to negative delta G, where delta G is equal to 0. This is where you're at equilibrium. At that equilibrium temperature at which you're crossing over from non-spontaneous to spontaneous, delta G is equal to 0. So consider that in this problem, where we ask, or we're told, water vaporizes, and its boiling point is 100 degrees Celsius. Its heat of reaction, this vaporization, is positive 40.79 kilojoules per mole. Find the entropy change of this reaction. All right, so we know that at 100 degrees Celsius, delta G is equal to 0. It's at equilibrium, at that boiling point. That's defined as being at equilibrium. So we can plug in for temperature as being 373 Kelvin, and we know our value of delta H. We know delta G is equal to 0. We can solve for delta S. Rearrange the equation and plug in to find delta S is equal to 109 just 109 joules per Kelvin mole. Thanks for watching, guys.